Okay, so before we start moving on to the actual sums and making it a bit more complex, we're going to start with a few examples just for practice, conceptualizing these estimates. So, question one. Given this curve, the first questions it says are estimate the value underneath it uh, using different using the left endpoints, right endpoints, and midpoints. Truth is, I can't draw that specifically, but I can explain how you would do it. What you would do is you would just have like a rectangle here, try and figure out what the y value is right there, and then just multiply by whatever x thing you have down here, like the length of that little rectangle. But since I can't do that easily, at least, I'm going to just show you kind of how to draw the rectangles on here. So, question number one that I'm adapting for it is L, or the left-hand sum, an underestimate or an overestimate of the area? What we can do is we can draw the left-hand sum onto here. So what happens? So remember, left hand is when you have a rectangle, and the top left corner is what touches your curve. So right here, down, touch the curve, 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 down, and touch the curve, down. So as you can see, we have covered the entirety of what is underneath the curve, but we have some space on top on all of these. That means our left-hand estimate is going to be an overestimate. We're going to have more than what is actually in the graph. Now, is the right hand an underestimate or an overestimate? Let's draw it on. We use purple this time. Put it right here. So for the first one, since it's mostly flat, it's going to be about the same. Right there. Down. As you can see, we have a lot of space left over. And just right there. We have a lot of space that we haven't covered with our curve, which means that this is going to be an underestimate, coloring some of that. So right here is uncovered by our right hand. So it's an underestimate. Now let's look at the midpoint one. What color should I use for this? Green. The mid. So midpoint cross right here, it's about the same anyways. Here, it's about the same. This is where it starts getting a bit funkier. So it's kind of, you can kind of see how it's between the right and the left. Maybe not because it's so far away. But right here, again, here, it's halfway between them again. Okay, so I want you to see what this is kind of doing. Our sum, or midpoint sum, is covering a bit of the inside and missing a bit of the outside. So it's missing some inside, missing some outside. Yeah, I'm right here actually. Missing some inside, missing some outside, missing some inside, missing some outside. It's kind of both. So you could say, or it's missing some inside and adding some outside. So you could argue that the midpoint in this particular case is actually the most accurate of the three sums that we can use. Let's move on to another question. Oh, all these require stuff. Estimations. This is really long. Okay, so this one's actually really interesting. So you remember how I told you that the way you calculate in your sum is by having your change in x. So ideally your change in x is consistent. You're going to have an n, which is going to be the amount of subintervals, n equals 7. the amount of subintervals you're going to use. And then A to B, B minus A over N is going to be your change in X. However, what if I choose an arbitrary change in X? Ooh, I got a message. Oh, I'm waiting for my chem exam grade to come out, but it has not been released. I'm going to draw you a table. I'm going to pause it so you don't have to watch it. Okay, I forgot to unpause. I'm sorry. Well, I didn't forget. I just pressed the wrong button. This is our graph, and we're going to evaluate the sum, and we have to do the lower and the upper estimate. And the way we do that is by using each of these data points as our heights. So we can see that the change in X is always going to be 0.5 for all of it. And so that's going to be the base of each rectangle on our graph. But the heights are what are important. So depending on whether or not it's going to be a right hand or left hand or midpoint, it's going to be the thing. Sorry. Yeah. So the way you do the right hand is you do this one, this one, this one, this one, this one, and this one, each times the change in X. But if you want to do the right hand, I mean the first one was left hand, the next one the right hand, this one, this one, this one, this one, this one, this one. Why? Because if you're on a graph, if this is X equals 3, if you have your right hand be the point, then you're calculating area that is outside your domain. But if it's left hand, it's going to be inside. Meanwhile, if you use 0, you're going to be calculating area that is also outside your domain. If you do the other estimate. Anyways, we're looking for the upper and lower estimates. I'm sorry I didn't unpause. I hope that was helpful as it could have been. And this is just the calculation. So 0.5 in every instance of this is the base times the height. So the first one is 0.5 times 6.7. Should have started with 0.5 times 0, yeah. Yeah, so 0.5 times 0 plus 0.5 times 6.7 plus 0.5 times 9.2, 0.5 times 15.5 plus 0.5 times 18.8 plus 0.5 times 19.8. And you add them all together and you're going to get the value you desire, which is going to be one of your estimates. This one is the right estimate, but it's left to be seen whether or not that's the lower or the upper estimate. We have to do the left hand to see if it's the upper. But first, I'm going to put these all together and see what the output is and if it's correct. Okay, so I was correct. I already knew that, but it's going to come out to be 35. So Rn is 35. That's our estimate. As whether this is the upper or the lower is yet to be seen. Now let's do our left hand. I'm going to change colors for this one. Purple. Purple, here we are. So the left is going to be using the left hand heights, which is going to be this one and all the way to the end. So to write it out, I'm just going to write change in X now instead of 0.5. I hope you understand. So 0.5 times 6.7 plus 0.5 times 9.2 plus 0.5 times 15.5 plus 0.5 times 18.8 plus 0.5 times 19.8 plus 0.5 times 20. This, I already added up just before, is going to give us a value of 45. And these are estimates. So we know that the actual distance she will have gone is going to be, can you actually see that? Yeah, is going to be between 35 and 45. Those are just the bounds that we have. So the answer for the lower and upper, well, this one's lower, so it's going to be the lower bound, 35 feet, and this is going to be 45 feet. Simple enough. Now I want to draw your attention to the fact that If these were uneven, let's say this was like 0.3, this was 1.2, this was 1.3, this was, I don't know, 1.9, that was 2.5, and this was 6. Instead of having a consistent change in x, what we would do is we would change which change in x we use every single time for our estimate. So let's get a new value for what we have. Some new estimates. I want you to pay attention to the change in x. So the change in x here is going to be 0.3. Change in x here is going to be 0.8. Change in x here is going to be 0.01. I mean 0.1. 0.1. Change in x here is going to be 0.7. Change in x here is going to be 0.4. Change in x here is going to be a lot. 4.5. 3.5. Yes, 3.5. So what do? We just plug them in. Let's say we're going to do the right hand. Actually, the left hand. Left hand's better because you use all the values. Equals 0.3, our change in x, times 6.7, plus 1.2, or 0.3 to 1.2 is going to be 0.8, change in x, 0.8 times 9.2, because that's our height. What's that? Okay. Now, the next one is going to be 0.1, because that's our change in x, times 15.5, plus 0.7 times 18.8, plus 0.4 times 19.8, plus 3.5 times 20. So the truth is this estimate is going to be wildly off, partially because I've been screwing with the values so much, but I just wanted to demonstrate to you the concept of what we would be doing. If you're given a table and your change in x is inconsistent, that's okay. Your estimate's just going to be really, really weird and off. Yeah, so you can add all this together and see what you get. I'm not going to do it because the number is irrelevant. Just the concept was important. And yeah, so let's continue on, see if there's anything else that's interesting. Mostly, oh, okay, here we go. Use this definition with right endpoints. Find expression. Oh, that's where we start getting into other interesting stuff. Okay, let's start getting into the notation of integrals. I'll see you in the next one.